Did you like the movie? Did you understand? If you understood it well, then you deserve a PhD right now. Before we start talking about gravity, I think this is the best place to start. These three pictures are taken from your book, from your textbook. Do you remember those? Of course. From left, look at the first picture. You can see the formula for gravitational force. F equals to Gm1m2 by d square. Related to this picture, I have a question for you. The question is light affected by gravity? Okay. First of all, make use of the fact given there. Light is massless. That is true. That is fact. Light is massless. Now, if you calculate gravity between, the force of gravity between Earth and light, I think you will naturally use that formula. Gm1 means mass of Earth, m2 means mass of light, divided by d square. If any of m1 and m2 is 0, what will be the net gravitational force? Yes, 0, according to this formula, right? Okay. Now go to the second picture. Have you seen that picture? Of course, yes. This is the famous experiment carried out by Galileo, right? Yes? A feather and a coin, when dropped from a certain height, falls simultaneously at the ground. Why does that happen? At this point, your answer should be, it is because when two things fall in the gravitational field of Earth, near the surface of Earth, they fall with same acceleration. And the value of acceleration is given by small z, which is approximately equal to 9.8 meter per second square. Since they have same acceleration, they fall at the same rate and hit the ground simultaneously. Is that enough? Yes. Now look at the third picture. It is taken from your exercise, from the textbook. What is happening there? When the rope holding the spring balance breaks, the suddenly spring balance shows 0 Newton. What is the reason for that? Weightlessness. Exactly. When something falls freely under the action of gravity, the object which is falling doesn't feel any kind of force acting on it. So it feels like weightlessness. Okay, now let's go to the next slide. We will come back to these questions later. Consider a train, right? Consider a train of length 1,86,000 miles or 300,000 kilometers, which is equal to 3 into 10 to the power 8 meter. Why I chose this number, you might be wondering. I chose this number because, as you know, speed of light is 3 into 10 to the power 8 meter per second. Right? So, consider there is a train of length 3 into 10 to the power 8 meter. Look at the video, please. What's going on? Yeah. Consider from one wall of the train, there is a flashlight shining on to the next wall, and the light travels from one wall to another wall. Now you answer me, how long will light take to travel from one phase to other phase of the train? 1 second, obviously, because the speed of light is 3 into 10 to the power 8 meter per second, and the length of the train is 3 into 10 to the power 8. So in 1 second, the light will reach from one phase to other. Fair enough. Now, here comes an interesting point. Now, what if the train is not at rest, but is moving at a constant velocity? The train is moving at a constant velocity. You can see there are two persons. One is red, one is purple. The red is inside the train, the purple is outside the train standing somewhere. Now we will see the event in the perspective of two. Look at the video, what's going on? Okay, the same thing is going on. Light is traveling from one wall of the train to the front wall of the train. And the train is traveling in a uniform velocity. Now you answer me in the perspective of Miss Red. Okay, in the perspective of Miss Red, how long will light take to travel from one phase to the other? Let me play once again. Will it take more than 1 second, less than 1 second, or again 1 second? Well, it is the problem in video that the light takes longer time, but in fact, the light again takes 1 second. What is the reason? Read there. Laws of physics are same at every train, at rest or moving with uniform velocity. What I mean to say is, do you play carom board? In one case you play carom board on ground, right? And in the other case you play carom board in a train which is moving with constant velocity. You must be very clear about velocity and acceleration. Are you clear about that? I assume that you are clear about that. Okay. So in one case, you are playing carom board on the ground, and in the other you are playing carom board on the train which is moving with constant velocity. Now you tell me, would you find any difference in your game while playing? Would you have to change your way of playing? No, because when something moves in constant velocity, unless you look outside of the train, you don't feel that you are moving at all. Moving at constant velocity is like not moving at all. Okay, when we regard such physical phenomena taking place inside the train. So are you clear till now? So when train is moving, in that case also, for Miss Red who is inside the train, the light will again take 1 second to travel from one face of the train to the other. Clear? Okay. Now comes an interesting point. There is Mr. Purple. He is standing outside somewhere and he is watching the train, right? He is watching the train. Now tell me, in the perspective of Mr. Purple, who is watching the train, who is watching the light flash going from one phase to other phase, will the light flash take again 1 second or more than that? Let me play the video. This is as observed by Mr. Purple. Okay? Now you will have to tell me, does light take again 1 second? No. It will take more than that. What is the reason? The reason is, okay, look at the point from where the flashlight starts in the perspective of Mr. Purple. Look at the point. Did you look at the point? Keep it in your mind, okay? Now I'll go to the previous video. This is Miss Red's perspective. Look at the point from where the flashlight starts. Are they identical? I think you did understand. Okay, look at this case first. In this case, in the perspective of Miss Red, the light is in the back wall of the train, say. Okay, so as the train moves in the uniform velocity, for her, it is like the train is at rest. There is no difference, okay? So, the light starts from the back wall and the wall is moving uniformly. Means, light still have to travel from one wall to another wall. No extra distance. No extra distance, okay? No extra distance. Now look at the second case. In the perspective of Mr. Purple. Okay. Now in the perspective of Mr. Purple, does light have to travel extra distance? Yes, because the light flash starts from there. Look at the left end. It doesn't move along with the train. So the light has to travel a longer distance, or the light has to travel for a longer time. Yes? Fair enough? Okay. Speed of light is always 3 into 10 to the power 8 meter per second. It doesn't matter where the observer is. Now this is the main point, okay? This is the most important point in relativity, that speed of light is always 3 into 10 to the power 8 meter per second. I'll give you an example. Suppose you are riding a bike. Imagine you are riding a bike at the speed of 50 km per hour. Imagine 50 km per hour. Now at the same time you take a stone and throw it forward at the speed of 20 km per hour. Now, if that stone is observed by somebody who is on the ground, what will be the speed of the stone? How much? No, 70, because bike is still running at the speed of 50 km per hour. You are at that bike and you throw a stone at 20 km per hour. So there will be addition of velocity. So when that event is observed by somebody on the ground, you will see that the stone will be moving faster, isn't it? How much faster? Means if bike has a speed 50 km per hour and stone's speed 20 km per hour will be added in that, right? So what will be the total speed as observed by an observer in the ground? 70 km per hour. But light is a different thing. From where you observe, this is the most important point in relativity. From where you observe, that doesn't matter. The speed of light is always 3 into 10 to the power 8 meter per second. So, for Miss Red and for Mr. Purple also, the speed of flash light is always 3 into 10 to the power 8 meter per second. Now, what does this imply? The speed of light is same for Miss Red as well as for Mr. Purple. But, listen, but at the same speed, there are two events, right? One event is the flash coming from back wall, and another event is the flash striking the front wall. The duration between two events for Miss Red is 1 second, whereas the duration between the same two events for Mr. Purple is more than 1 second. How come is that possible? This is possible only when the time runs slower for Miss Red. If time runs slow for Miss Red, then only that will be possible. Think about it, okay? So here comes a very interesting conclusion. The conclusion is, when something moves at great speed, and remember, you can observe this effect only at very high speed, not at usual cases. We haven't been observing it in our daily life because we don't travel at that high speed. So, when something travels in very high speed, the time runs slower. The time runs slower. Okay. Now we slowly go into the gravity, okay? Look at those two pictures. Look at right hand side. Look at right hand side. You can see Earth. Somebody is in a lift. He is dropping a stone downward. Acceleration due to gravity is downward. Earth is pulling everything downward, right? Now, on the left side, imagine that there is no Earth, there is no gravitational force, nothing. You are in an outer space where there is negligible gravitational field. But in that case, the lift is going upward. The lift is going upward with an acceleration equal to g. That means 9.8 meter per second square. Now listen to me. In these two cases, the man who is standing inside the elevator will feel the same thing, will feel the same downward pull, and the bulb which he is holding, if he leaves it, it will fall in the same way. Let me repeat that. In the right hand side, it is on the surface of Earth. Left hand side on the space. But the difference is, on the left hand side, the elevator is moving upward with an acceleration equal to small g. And on the Earth's surface, there is acceleration due to gravity small g. You already know that. So if we can apply the same acceleration in upward direction, everything will be same. I mean to say is, now you are creating an artificial gravitational force, gravity which is equal to the gravity provided by Earth. So here comes the conclusion for this picture. The conclusion is the effect of gravity and the effect of uniform acceleration is same. Effect of gravity and the effect of uniform acceleration is same. Now let's move on to the next slide. I will show the same events in a video file. Look at the video, what happens. The man is holding a ball, he will release it, and the ball will move downward, slowly. Look at those two pictures. Is there any difference? Is there any difference? Only difference is, in left side, the elevator is moving upward with an acceleration of 9.8 meter per second square. And in the second one, the elevator is at rest on the surface of Earth. And the Earth applies an acceleration of 9.8 meter per second square. But for the person who is inside the elevator, there is no difference at all. Everything is same. The ball falls in the same way and the ground pulls him in the same way. So, accelerating frame of reference. Okay, let's not use any technical terms. The effect of acceleration and effect of gravity is same. This is known as equivalence principle, for your information. If you don't remember, that's fine. See what's happening. What did you see? Okay, a man is in an elevator. He is shining a light from one wall to the other. The light is traveling along my straight line. Fine? Let me play it again. Yeah. But now what's happening? In the second case, the elevator is not at rest, but it is moving upward. Moving upward with an acceleration, with a uniform acceleration. For your information, acceleration is the rate of change of velocity. When velocity becomes more and more every second, that process is known as acceleration. So if elevator accelerates upward, what happens? The ray of light will be bent. Let me repeat. When he shines the light from one wall to other wall at rest, the light moves straight. But if elevator is accelerating upward, the light will bend. The light will bend. Now remember, just in the previous slide, what we proved? In the previous slide, we proved that effect of acceleration and effect of gravity is same, right? Effect of acceleration, uniform acceleration, and effect of gravity is same. And in this slide, you saw that acceleration bends the light. Now guess what? Gravity also bends the light. Gravity also bends the light. So my first question was, from the formula F equals to G m1 m2 divided by d square, will gravity affect light? What did you say? No, because your formula said so. If you use that formula, of course not, because light is massless, so answer should be 0. But in fact, that is not the reality. Reality is gravity bends the light. So what is the conclusion? Was that formula wrong? Was that formula wrong? Yes or no? Actually, we can't say that that formula is wrong because now also that formula is being widely used for launching satellites and all. But when we consider the case of light, yes, that formula is wrong. So we need a different definition of gravity. This is the reason why Albert Einstein came up with a new theory of gravity. Okay, now let's look at these two pictures. The man on the left hand side is in an elevator which is accelerating upward with a uniform acceleration A. And the man on the right hand side is on the surface of Earth who is not moving. But the Earth will be providing an acceleration due to gravity. The value of acceleration is same in those two cases. Look at the video. What is happening? An accelerating elevator. Elevator is accelerating upward, light is bending downward, right? And on the right hand side also light is bending. Okay? If you shine a light here on the Earth's surface, light is bending, yes, but by very less amount that you cannot detect. If Earth was so massive and so dense, in that case, what would happen? I told you before, you could see USA from here. Probably light would bend from USA to here and you could see there. If Earth was so dense and so large. So from here, what we proved is gravity bends the light. Okay? Now what is it? I told you gravity bends light, but light has a feature that light is something that takes the shortest way. Yes? That takes the shortest way. For example, I take a torchlight, shine from here to that wall, and I tell all of you to go from here to there. Who will take the shortest way? The light ray will take the shortest way because you've been learning that light travels along straight line, so straight line will be shortest. Yes? But that's wrong. Straight line is not always the shortest way. Let me give you an example. On the surface of football, imagine there is an ant. Did you imagine there is an ant? Yes. Now you tell that ant to go to the opposite side of the football. Opposite side of the football. Now what happens? And the ant has a condition that it should take the shortest way. It should take the shortest way. Then will it travel along a straight line? How will it travel? It will travel along a curve. Along a curve. Isn't it? So on curved surfaces, shortest distances are not straight lines, but they are also curved. By our previous video, we proved that light curves in gravitational field. Why does that curve? Because light always takes the shortest way, and the shortest way is curved. What does that imply? That implies that our space-time universe, say, our space-time is not flat, it is curved. Our space-time is curved. Now what's going on in this video? See. Look at the video, please. What happened? Look, there is sun in the middle. Okay? This is Earth, and that is far away star. That is far away star. What happens is, let me replay it. What happens is, when light comes from that star, the sun's gravity will bend it. Why will it bend? Because the space-time around sun will be bent and the light will take the shortest way, and that shortest way will be a curve. So the space-time is a curvature. It is the conclusion for this slide. Now look at some examples of space-time curvatures. First, look at sun. Sun is shown in a space-time. It is causing the space-time to curve, right? As you can see. In the second case, you can see white dwarf. It causes more distortion. You know why? Because white dwarf is denser than sun. And you can see neutron star, even denser. So space-time is even more curved, distorted, right? And in that last picture, you can see that is the picture of black hole. You saw black hole in the movie, but that was quite different from this, isn't it? That was the view as seen from your eye, right? Or by a camera. This is the view, how space-time is actually, oriented, right? So here what happens? Black hole makes a curve, makes a distortion in the space-time. Okay, so you can see there event horizon. Did you see event horizon? What is event horizon? Do you have any idea? Okay, let me tell you. Event horizon is a region. If you cross that region and go into the black hole, you cannot return back. Okay, beyond event horizon, everything is absorbed by a black hole, so not even light can escape out. Okay. For details, you can search in the Google and learn more about black holes. Okay, these are very interesting things. Once you get interested, you will learn more and more. Now, wormhole in the movie. Please recall, in the movie there was a wormhole. What is that wormhole? In simple words, wormhole is a shortcut from one place of universe to the other place of the universe. In the movie there was shown that they are traveling from one galaxy to other galaxy. Traveling from one galaxy to other galaxy requires a great amount of time. Okay, one man cannot complete that in his lifetime. Okay, but traveling along wormhole can make it possible. Theoretically, wormholes are possible, but till now, none of human beings have traveled through wormhole. Read about it more on the internet. Okay, thank you so much. This is the end of today's talk. And one thing I would like to tell you, listen, just one thing. I know that for most of you it was very difficult to understand. And I must admit that even I haven't understood Einstein's theory of general relativity and gravity thoroughly. Okay? So, if you didn't understand, that's fine. But if you developed a little bit of curiosity to learn about these things, then my job is done. I am successful today. Okay, thank you so much for your patience.